Thank you.
Great. So our next talk this morning is from Mukesh Singh, and I will just hand over straight to you. Take it away.
Thank you. So let me introduce first myself. I'm Mukesh Kumar Singh. I'm a grad student at ICTSDFR, Bangalore, India. First of all, thanks to the organizers for providing me the opportunity to talk about my work on associating fast radio bursts with compact binary mergers, gravitational lensing. Okay, so to start with, fast radio bursts are nothing but bright radio millisecond duration radio pulses, which are being observed out to cosmological distances. Since the first discovery of first FRB in 2007, we have not been able to identify the origin source of these radio bursts. But thanks to the advances in the field of building new telescopes, radio telescopes, as you can see in the bottom, the CHIME telescope, the Canadian telescope, we are observing dozens of FRBs per day, and that has thrown some light on the kind of distribution of these FRBs. For example, some of the FRBs being observed are repeating FRBs, which are suggesting that the magnetars are as sources. Now, there are some alternative models also, which are especially for non-repeaters. For example, the mergers of compact binaries, which emit gravitational waves along with the fast radio bursts. So among these proposed CBC models, CBC stands for compact binary coalescence for FRBs. Here are a few which I mentioned here. For example, the magnetic braking of synchronized magnetic fields in binary neutron star mergers can also lead to such kind of emission. Then there's magnetic reconnection in the final stages of binary neutron star BNS in spiral due to the interaction of the toroidal magnetic fields. Then there can be interaction between the two neutron star magnetospheres that could produce repeating FRB-like emission, even decades or centuries before the final plunge. There are also models that suggest that a neutron star black hole could also produce an FRB type signal if mass ratio, which is the heavier mass in the binary to the smaller, the lighter binary, which is greater than 5. This can actually lead to FRB type signal emission. Given this mass ratio constraint is because in this case, they're highly unlikely that there will be any tidal disruption, hence that will negate that will absorb the FRB signal from the binary. Also, the collapse of remnant neutron star from the merger of a BNS into a black hole could also produce the FRB. A reason being that as the magnetic field lines snap as they cross the black hole horizon, and this time at which the FRB is being emitted after the merger can be highly uncertain. It can be of the order of 10 to the power 4. Also, somewhat speculated model is that inspired of a pair of spinning black holes could also produce a Poynting flux if at least one of the black holes is charged. This is based on the fact that the charge in the black holes could produce or could induce a global magnetic dipole that could lead to the emission of FRB when they merge. Okay, so LIGO Virgo have been looking for these associations. So till now, they have searched for temporal and spatial coincidences of gravitational waves from these CBC mergers with the FRBs, but they have not found any confident associations. But the associations cannot be ruled out confidently. The reason being the poor measurement of various extrinsic parameters of gravitational waves as well as fast radio burst. So what are these limitations of current searches? One of them being that there are large uncertainties in the estimates of distance in gravitational waves as well as FRBs. in the case of FRB, this is primarily because of the poor understanding of the dispersion measures. This is a quantity which quantify the integrated column density of free electrons along the line of sight from the FRB source to the telescope. That you can also see on the plot on the right hand side. I don't know if the levels are visible here, but the black horizontal lines here represents the 90% credible error bars on the measurement of luminosity distance from the FRB, and the color bar here, blue, orange, and sky blue, that corresponds to the horizon distance of gravitational detectors for BNS and NSPS systems. So there's an overlap, but due to large uncertainties, you can't really say whether there's any association. Now, not only that, there's a poor localization of gravitational waves. This can be of the order of a few hundred square degree, even bigger than this. Now, on top of it, there's a poor understanding of the time delay between the gravitational wave or the CBC merger and the FRB emissions. So that actually limits our capability to search these kind of associations. Also, at the moment, as you can also see from the plot on the right-hand side, the lower horizon distance of gravitational detectors limits the ability to search for associations of distant FRBs. So what else we can do? We propose the idea that using the gravitational lensing of both gravitational waves and FRBs, we can make more confident associations if this hypothesis that FRBs are being emitted from a CBC merger is true. So in the cartoon on the right-hand side top, you see there's a gravitational source merging, and there's a galaxy acting as a lens, and you get two copies of same signal, but it is rescaled in the amplitude. This happens in the case when the size of the lens is very, very greater than the wavelength of the source which is emitting the signal. So in case, this is called the strong lensing regime. So when both GW and the FRB wavelength are very, very smaller than the size of the lens, you will get two or more identical copies of gravitational waves and as well as FRBs, but they will be rescaled in the amplitude. So on the top, you see the two copies of GW signal. In the bottom, there's a cartoon showing the two copies of FRB also. But since these are the lensing of these GWs and FRBs can be independently identified, hence they will give us the time delays. So the most crucial point in this presentation is that given these independent measurement of time delays, can we make an association by matching these time delays to associate whether the FRB is related to the particular CBC? Well, this kind of association will not only be applicable to FRBs, this can also be applied to GRVs, gamma reversed, and also other counterparts. So just to quantify the numbers, like how confidently we can make such associations, we choose a distribution of a population of NSPS systems, and we find out, given the current design sensitivity of gravitational detectors, we find out the intrinsic time delay distribution of lensed gravitational signals, which is shown in the orange curve on the right top plot. And but since this will be affected by the selection effects of the detector, so we apply a threshold of the SNR, network SNR in the detector should be greater than 8. In that case, you end up with a blue curve here, which is the detected lensed time delay distribution. Now for this preliminary results, we have chosen very simplistic lens model, which is singular isothermal sphere, and lenses are being drawn from SDSS survey, which are galaxies. Now we ask the question, suppose we observe a lensed FRB, what is the probability that we can falsely associate with at random with a observed lensed NSPS system? And we find that the probability is very, very small we have done this analysis in the bottom. You can see in the bottom, the 4,000 NSPA systems, the probability is of the order of 10 to the power minus 8 to 9. So this means that we can even associate this FRBs with a greater confidence of 5 sigma. Now, this false alarm probability will scale linearly with the number of lensed FRBs detected. Now, time delay distributions of FRBs will be affected by other selection effects rather than just magnitude limitations. Like, for example, in gravitational detectors, you have just SNR as a threshold. For FRBs, that's not the only one. There is, for example, there will be intervening matter in the line of sight, and also because the source spends finite duration of in the field of view of the telescope. For example, in case of chime, which is if telescope fixed on the Earth, it is rotating with the Earth. So source will only spend a few minutes to hours in the field of the telescope. Now, in this case, we make a very crucial assumption here that we assume that both FRB and GW detectors have same horizon distance. What it means that they will have similar time delay distributions for all sky detected lensed events. When I say all sky, that means distributed all around the sky. But so since the GW detectors are all sky, they will be observing all time delays. But the radio telescopes are not. So we have to account for that fact. Now, after accounting for that fact, so if you see in the plot on the right-hand side, this is highly preliminary here. So the blue histogram denotes the time delays for FRBs when you assume that they are all sky and you do not consider the finite field of view of the telescope. But when you take into account the finite duration of the source in the field of view of the telescope, you see that the only smaller time delays are being observed by the telescope. And this fraction of time delays for FRBs that can be associated with the NSPHs is of the order of 0.5%. But again, there are a lot of uncertainties here. This number should be taken with a pinch of salt here at the moment. Now, not only the strong lensing, but there's something called microlensing of gravitational waves that can also lead to such kind of associations. So in the case of microlensing, which happens when the GW wavelength is approximately of the size equal to the size of the lens. In this case, lens can be intermediate mass black holes and also compact dark matter halos. This will fall in the wave optics regime, and you will see the lensed waveform will have some distortions. So that is happening because the time delays between the two copies of the images are so small that they're kind of overlapping with each other, and you see a distorted waveform. But since the FRBs have again still very small wavelengths, so they will still fall in the strongly lensed regime, and you will have two identical copies for FRBs with amplitude rescale. Now, given the distortion in the GW waveform, you can actually measure the lens mass, which is causing these distortions, and also the impact parameter that can further lead to the estimation of time delays observable in FRBs. So again, predicted time delays from GWs lensing, you can compare them against the FRB time delays. So just to explain, so giving an example for a micro-lensed gravitational wave with strongly lensed FRB, on the right-hand side, I've chosen a BBH system, binary black hole merger, with a lens mass of 2,500 solar mass and an impact parameter of 0.4. And what I'm showing here is the posterior probability distribution for time delay, which is estimated, inferred from the GW lensing. And the yellow line here that corresponds to the distribution or uncertainty distribution for the FRB time delay peak measurement. And this is very precise because the time measurements in case of FRBs are high, like in the of the order of uncertainty of the order of nanoseconds. So this looks like a delta function. But what you can take from this plot is that the time delay measurement of lensed FRBs is are well within 90% credible interval of lensed GW measurements. On the bottom left plot, I'm showing here the time delays or the uncertainties in the measurement of time delays for 10 binary black hole mergers in the microlensing region. So on the y-axis, you see the time delay, median of the time delay posterior, and on the x-axis is the true value of the time delay, and the color bar here represents the uncertainties in the measurement. And what you see here, that the uncertainties are of the order of less than milliseconds. So that is good for the association for FRB type signal. Moving on, not only just association, we can also do a sub-threshold search. For example, if a lensed FRB is detected, sorry, there is a typo here. I should have written, if a lensed gravitational wave is detected and one FRB image is within the coincident time window of the GW, that means you do not see the other image of the FRB, and that might be because it is sub-threshold, it is not being detected. So then you can do a sub-threshold search for the second image of GW, which is associated with the second FRB image. Similarly, you can do similar thing with the lens GW detected and one FRB associated. You can search for the second FRB image. Same idea can also be applied for gamma ray burst, but with the caveat that it is not going to work for in the microlensing because the time delays predicted by the GWs are larger than or smaller than the signal duration of gamma ray burst. So just to summarize, so using the time delay measured for the lensed gravitational waves and FRBs can be used to make a confident association greater than 5 sigma for the hypothesis that the FRBs are being originated from CBC mergers. Similar can be done with microlensing also, microlensing of gravitational waves from CBC mergers. We can also do sub-threshold searches if either lensed GW or FRB is identified to search for the second counterpart image, which was sub-threshold and was not detected. We can also put some constraint on the time delay taken in the emission of an FRB after or before the CBC merger, which is not well understood at the moment. In future, we intend to compute this time delay distribution for more realistic lens models. So currently we were choosing a singular isothermal sphere, which is not a realistic scenario. In reality, we have galaxies, which are more like an ellipsoid. So we are planning to use singular isothermal ellipsoid and then see how these numbers change. So I will end with this and thank you. I will take any questions if there's.
Thank you for a very interesting talk. Let's throw it open for questions. Okay.
Hey Mukesh, thank you for your interesting talk. Could you go back to the slide where you had the summary of all of the models that could actually explain the FRB signal and as well as the gravitational wave signal? So we of course have both repeating and non-repeating FRBs, and while you were going by, I was struggling to see which of these models can explain both repeating FRBs and non-repeating FRBs at the same time, or if it's really the case that we're saying that there are two populations already, and yet somehow both are also being affected by gravitational waves and gravitational lensing.
Yeah, so if I understand your question correctly, so in case of these mergers, in most of the times, they are the cataclysmic events are happening just only once. For example, the merger of binary neutron star, the magnetic fields are coming closer, and they merge. That can lead to emission of FN FRB. So that will only emit a non-repeating FRB. But there are some papers which suggest that if the neutron star has magnetosphere and large magnetic fields, due to the interaction of these magnetospheres, fairly before the merger, even like decades, they mention even decades before the merger, that can lead to the repeating FRB-like emission.
And just a quick follow-up, as far as I understand, the properties of the repeating versus non-repeating FRBs are very comparable, other than the fact that the repeating FRBs repeat. So we're really saying here, despite the fact that the properties are very similar, there are actually two physical mechanisms?
I don't think we can say that confidently because they are highly similar, right? I'm not sure if I can answer that question. Yeah. Sorry.
Great. We have plenty of time for more questions. Okay.
I have
we have a question online.
yes.
Great. Thanks for speaking up. I didn't spot you. Martin, over to you.
Yes, thank you. I'm Martin from San Martin University in Argentina. So do you have an estimate of the rate of the lensed fast radio bursts, or what's the fraction of FRBs that will have a measurable lensing?
So actually, I did mention this number on the slide. So if we assume that, so this is for SIS lens model, which is not realistic. And so assuming that lens model, and we try to incorporate the selection effects due to if the source is spending a finite duration in the field of the telescope, because telescope is moving. So there's a relative motion between the source and the telescope. So you will only be able to see only shorter time delays, although gravitational signals can have time delays, even as you can see in this plot, even days and even like 100 days, those are expected. But you're not going to see those in the FRB because of the limitation of these radio telescopes. So assuming that only that selection effect, we find that only 0.5% of the FRBs that can be associated with, assuming the NSPH only mergers. So we have not done the BNS or BBH cases yet.
Right. Thank you.
Great. I think I saw a comment popping up on the chat from Timo. So if you're still with us, Timo, you're very welcome to speak your comment.
Hi, everyone. Yes, I was just wondering about this repeating versus non-repeating fast radio burst. I understand the monitoring for these things hasn't been that long, so maybe those non-repeating haven't repeated yet, or am I wrong?
Yeah, that is likely true. If the repetition is have a larger duration, then you're right.
Thanks.
I have a quick question for you. I'm
Okay.
curious how many FRBs have been detected so far.
So it's the order of a couple of hundreds, I would say, maybe even more than 500.
Okay, and is there any evidence for any of them being lensed so far? I believe I haven't followed the literature recently, but there has been a little bit of discussion, I think.
No, currently there's no confident lensing detection in FRBs.
Okay, interesting. Okay, well, do we have any more questions in the room or online? Gautam has a comment.
I was just
Yes.
responding to Timo's comment in chat there. I thought the baseline for some of the oldest repeating FRBs was something like 2012. If I remember, it's like 121102 is an FRB that repeats and happens to be one of the first ones that was found, probably because it repeats. So, I thought most of the periods were fairly short, but I don't know. This is not, certainly FRBs are not my field of study. I am certainly curious because I have to update my slides for introductory astronomy if I'm wrong, so that we tell our students the right things. But it'd be surprising to me, I guess, if there are extremely long period FRBs that are somehow lurking in the sample, and then there's just a massive gap between the extremely long period ones and the ones that we've already found, which are generally pretty short period.
Yeah.
Thank you, Gautam, by the way. I always thought it was 10 years, the monitoring, but I never thought, I thought repeating might have been once every 4 years even. So I don't know, if it's shorter than that, then you're right.
Yeah, just to add a comment on the repeating FRBs. So although they are repeating, there's no definite period between different images. So yeah, it can very well be like lensed FRBs or multiple images, but certainly they can't be like 10 images, which was in the case of this first repeating FRB observed.
Sorry, but just to clarify, what's the typical period of repetition then? Do you have a mode? Is it a day or is it 4 years?
Repetition, although I'm not very sure about it, but from the first event or first FRB, I understand it was of the order of milliseconds, if I'm not wrong. Hours. Okay, sorry, I don't know actually. But again, the lensing can also give you time delays of minutes to hours.
Great. So thanks everyone for an interesting discussion, and let's thank the speaker again for a really wonderful talk.